Well, I was hoping to be back by now, but here we are. So, with this week we will just be doing the uh, the spinach lab, but I'm going to go ahead and start with our chapter 14. So we'll be doing the spinach lab. We'll just be pushing things back a week. I might update the syllabus, but for now, just pushing things back a week. We're just hoping we don't miss Wednesday as well, because it's really going to screw things up. Okay, so conjugation, resonance, and dienes. Conjugation, resonance, and dienes. So the idea here, we're really going to hit on conjugation. Remember, conjugation occurs when we have p orbitals that can overlap between three or more adjacent atoms, which causes our resonance. So we can have, as you see, a 1,3-butadiene. So we can have like the p orbitals on the two alkenes. They're both pointing. They're all pointing in the. In this case, this would be what, like, if the flat plane is the x and the y plane. There's pointing. They're all p orbitals in the z-axis. We can have the allylic radical that we just talked about last chapter. Well, we have p orbitals. We have two p orbitals in the alkene bond and a empty p orbital. Well, not really empty orbital, but a p orbital that contains a single radical. And we can also have a allylic cation and allylic anion, where we have an empty p orbital that we can see electron transfer, and we can have a filled p orbital where we can see electron transfer, where we're pushing electrons one way or another. But the idea of these conjugation causes the delocalization, which will lower the energy and thus stabilize the overall molecule. Now, the key thing here is that the sp2 orbital needs to be between them. If there is a sp3 atom between these pi bonds, they are isolated alkenes, and we see none of the stabilization. But so long as there's an sp2 or even an sp orbital between these, we can see this conjugation. Now, the delocalization occurs with any charged or radical allenes. This primary allene has stability that's similar to a secondary carbocation. So even though we would say primary carbocations are very unstable, this guy is about as good as a secondary, as you can see down here. So the methyl, lowest stability, the primary second, then we have secondary and allylic, and the tertiary cation is the highest. Now remember, in radical stability, the this allylic radical was higher than the tertiary. But in the terms of carbocation, it's below the tertiary. Now, resonance requires delocalization of the pi bonds or non-bonded electrons. So it could form in many different things, but there's certain cases. So we can look at a generic reaction here. Generic example: X double bonds to Y, and we have a Z, and Z star, and we could resonate to X star, single bonded to Y, double bonded to Z. Now that star could be a cation, it could be an anion, it could be a radical, or it could just be a non-bonded lone pair. All these situations will allow this to occur. The key is that starred atom has a p orbital on it. this could be allylic if X, Y, and Z are carbons, but these X, Y, and Z can be heteroatoms. So in the case of down here, we see a carboxylate, where so X and Z are oxygen atoms. And we're moving an anion lone pair, anionic lone pair between the X and the Z. Now, other examples of resonance could include conjugated or double bonds. The simplest one is an aromatic group, which we'll talk about more later. But aromatic group where all the double bonds can swap around. But even in the case of a 1,3-butadiene, we can see resonance. Now, is this resonance structure necessarily the most stable? No. But you can see this, that we can resonate to form a carbocation on carbon 1 and a carbanion on carbon 4 with an alkene between them. And we can resonate to the reverse. Other examples can see just a shift in a lone pair and cation. So in this case, the most common example is a carbocation adjacent to an oxygen. We can see it shifts from the cation on the carbon to the cation on the oxygen. This is an example of resonance. And of course, the one we will see probably most commonly going forward is this double bond with an electronegative atom that we can shift up and form a O- and a carbocation. You should really, really pay attention to that one, that this carbonyl carbon is particularly electrophilic, and this oxygen on the carbonyl is particularly electronegative, that if we attack with an electrophile, it's going to attack the oxygen. If I attack with a nucleophile, it's often going to attack that carbon because of this resonance structure, Now, for this to be true resonance, there are some rules we must follow. The resonance hybrid will always be a combination of all possible resonance structures. But the resonance hybrid will most closely resemble the best resonance structures. So if you can choose major versus minor contributors, you can see which the structure will most closely resemble. Rule number 1. There's other rules that will make more sense, that will make it also make more sense, but the more bonds and the fewer charges a resonance structure has, the better it is. So in our carbonyl situation, that double bond that is uncharged is better than the single bond with 2 charges. The butadiene, the 2 double bonds with no charges is better than the double bond, 1 double bond and 2 charges. But rule 2, giving more octets is always a better resonance structure. So even though you're like, well, it seems like you would want to give the oxygen's negative and the carbon's positive, it's better to have the carbon and the oxygen have an octet than the oxygen to be neutral with an octet and the carbon to be non-neutral. The carbon to not have an octet. So in the case of our methyl cation adjacent to the oxygen, it's better to form the double bond to the oxygen and give the oxygen a plus and keep the carbon with an octet. However, if a negative charge has to be placed, placing it on the more electronegative atom is preferable. So having a carbanion versus a oxygen and oxyanion, you'd prefer the oxyanion. So the resonance, like both atoms will have an octet in both resonance structures. It's better to have the oxyanion in this case. Another argument for in Rule 2, if you look at it, we have more bonds. 1, 2 bonds versus 1, 2, 3. But here we go. 1, 2, 3, 4. 1, 2, 3, 4. It's better for the oxygen to have the anion. Now, resonance requires the delocalization of electrons. To do this, we need unhybridized p orbitals on all the atoms within that resonance structure. Basically, the atoms must have adopted an sp2 or sp hybridization. Because remember, the orbitals are s orbitals, which are our spheres, and our p orbitals, which are our double lobes. When we make sigma bonds, typically these s and p orbitals are hybridizing into these weird, like, asymmetric lobal things, the sp, sp2, sp3 hybridization, that uses up the S and the P and combines them to make single bonds. And we combine them in such a way to make the hybridization represents how many single bonds must be made. And they also represent the shape. So if I only need to make 3 or 2 single bonds, that means I only use the S and the P or 2 of the P's. And that leaves a third P that's capable of being unhybridized and thus doing our stuff. So, even though sp3 hybridized orbitals are lower in energy than an unhybridized p orbitals, so p orbitals are up here, s are down here. When we hybridize them, s goes up, p goes down. So you would have sp2 right here, and you'd have the p right there. The delocalization effects will stabilize the compound more than having an sp3 hybridization alone. So the idea here is that the molecule is always trying to save energy. The molecule is always trying to save energy, while the sp3 hybridized orbitals are lower energy. If you can unhybridize the p, it saves more energy than if you just made it all sp3 hybrid. So thus, sp2 or even sp1 hybridization is preferred in atoms within a system that is capable of resonance. I want to jump back real quick, looking at this middle guy. Because normally when we think of oxygen atoms, we think sp3 hybridized bent. We think of sp3 hybridized bent structure because that's how we think of most water molecules and what have you. But what we just said there is that because of this delocalization effect, this oxygen atom in the center is actually sp2. Still bent, mind you, but one of those lone pairs is in a p orbital above the oxygen. And that's how it has to be. So in all of these structures, sp2 sp2, sp2. Even though you might want to say this oxygen down here is sp3, it still remains sp2. This guy's sp2, 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 sp2. So what's that is saying? Rather than adopting an sp3 shape, it is adopting sp2 in order for this to work. One of our major factors in here is we're going to look at conjugated dienes in this chapter. 1 to 3 dienes specifically. So 1,3 dienes can exist in several different stereoisomers and conformers. So remember, stereoisomers, we cannot rotate them to get different shapes, but conformers are different shapes of the same molecule. So looking at this, we can have a trans-trans, a cis-cis stereoisomer, or a mixture of cis and trans. But in terms of conformers, we can rotate that central bond and get what's called an S-cis or an S-trans. All these structures that you see in the top right are S-trans. But you will see different down there. So while stereoisomers are locked in the shape, the conformers can interconvert. However, there's usually a different energy value, similar to the concept of staggered and eclipsed. If you look at the case of the trans-trans, this is preferential to remain in the S-trans. So trans-trans, S-trans, because if you allow this to shift into the S-cis, you get the two alkyl groups adjacent to each other. And so this is a high energy system. But if you have in this case, a cis-cis, and you have it in the S-trans, it's not really affecting it. But if you allow it to shift into the S-cis, they are away from each other. And so this is not a very high energy system. So that's not a big issue. But so it's where these alkyl groups can get in the way of each other. It can make shifting difficult. Now, some notes on the butadiene. The notes on the butadiene. The idea here, and the carbon 4-carbon bond. Some notes. The carbon 2 to carbon 3 is a sigma bond, but it is shorter than most carbon-carbon single bonds. Where most carbon-carbon single bonds are 153 picometers, it's 148. And that's because both carbons are sp2 hybridized. And so they have more S character. That in general, conjugated dienes are far more stable than isolated dienes. This can be shown by looking at the enthalpy of hydrogenation. How much energy is generated from the enthalpy of hydrogenation. It's like how much harder is it to hydrogenate. So if it's an isolated diene, we can get 255. If it's a conjugated, we only get 226, meaning there is about 29 kilojoules of stability in having a conjugated diene. And one of the other major things is that conjugated dienes can react differently than normal alkenes. While they will react in the same way as alkenes can react, they can also have additional reactions brought about by conjugation, especially conjugation in slow steps. Now, conjugated dienes will actually absorb a longer wavelength of ultraviolet light. Now, there's a whole field of spectroscopy where you can use the length of light and the substitution, the length of the double bonding, and the substitution on these conjugated double bonds to actually calculate what light it should absorb, but it is a whole mess. So I'm not going to, it's not as useful as infrared is. It's not as useful as NMR and mass spec is. So I'm not going to teach how to calculate the ultraviolet light predicted for these guys. But you can. But the big thing, so the big equation, the new thing we can look at is the effect of electrophilic addition to 1,3-butadienes. In a isolated diene, you simply get Markovnikov addition to a single alkene if you add one equivalent of HBr. If you add two equivalents, you would add it twice. But so, remember, how did this occur? Markovnikov addition first adds, the diene attacks the hydrogen, thus forming a carbocation on the secondary carbon and a bromine anion. The bromine anion now attacks the carbocation. Now, if I add one equivalent of HBr to a conjugated diene instead, I get a mixture of products instead of simply Markovnikov, which would be 1,2 addition. We get Markovnikov and a new 1,4 addition. So we get a Markovnikov addition, but we get a secondary byproduct. And that is coming from the idea of a conjugated allylic carbocation. So we form a carbocation on the secondary carbon. Conjugation allows to move the secondary carbocation to a primary position on the 4 carbon. And thus bromine can add both to the secondary carbon or the primary carbon 4. The mechanism is not dissimilar to what we would have seen in an isolated diene. It's just that resonance allows this to change. So while we will form a mixture of products, this is not an equal percentage of 1,2 and 1,4. There will always be a major and a minor byproduct, a major and a minor product in these situations. However, the beauty is that we can control the amounts of each by the conditions we will run these under. And this is one of the features we will talk about. Kinetic versus thermodynamic. One product will be faster to form for obvious reasons. One product will be more energetically stable, as we'll discuss in a minute. So, under fast conditions, you run this so that you can run the reaction so only a fast product will form. But under the conditions of thermodynamics, you run it for a longer period of time and allow the stable one to form up. Now the 1,2 is the fastest. 1,2 because the sheer reason of having a carbocation, a secondary carbocation, is more stable. Even though it's resonating, a secondary carbocation is more stable, so we have a lower energy barrier. Also, you can make it from the argument of we've just attacked the primary carbon has just attacked the hydrogen. The bromine is going to be more closer to carbon 2 than it is to carbon 4. So one of the ways we can favor forming the 1,2 product is running this under a very cold temperature. So cold temperature means the reaction goes slower, and only reactions that have enough activation energy, enough energy to overcome the activation energy barrier, is going to form. And so it favors kinetic product. So it goes over this small hump of activation energy barrier 1. So you can get an 80-20 mixture. So running at really cold temperatures favors only the fast guys. We're only allowing the fast guys to form. Now the thermodynamic product. The thermodynamic product is the 1,4. And why is this? The 1,4 product is more stable because of producing a more substituted alkene. A monosubstituted alkene is lower in stability, is less stable than a disubstituted alkene. And so even though a primary carbocation is less stable, a disubstituted alkene is more stable. And so this produces, so if we allow more time and more energy, we can favor the 1,4 addition. So this is enthalpically favored, meaning it's a more exothermic reaction. It has a higher activation energy barrier to form, but when it does form, it releases more energy and it's harder to reverse. So this is controlled by equilibrium, our K, capital K. So by running this at elevated reaction temperatures and longer reaction times, we can favor more thermodynamic products. Now, because everything is hotter, you will get initially higher amounts of the kinetic product. But because everything is hotter and has more energy, the idea is that bromine can actually fall back off. That bromide can fall back off, and so we can reverse it from the 1,2 product back to that intermediate. And eventually, enough of the intermediates forming that we'll go to the 1,4 that you get the ideal mixture. So the idea here is that the reaction is reversible at high enough temperatures. And if it's reversible, we can favor more of the 1,4 product. And so it's like by controlling conditions, we can favor one reaction versus another. So as I said, the 1,2 product forms faster due to a proximity effect. And once the pi bond attacks the hydrogen, the bromide ion should be closer to the second carbon than the fourth. 1,4 is more stable because of the substituted alkene. So at low temperatures, basically I'm just repeating what I said. At low temperatures, the activation energy barrier factors more heavily. Molecule motion, mixing is slowed. Molecules have greater difficulty overcoming higher activation energy barriers. Once product is formed, reversibility is low, so equilibrium is not allowed to establish. At high temperatures, reversibility is the major factor. Equilibrium is allowed to establish, so once the reaction with more large enthalpy forms, it's difficult for that to reverse. So we will stop there. We will look from beyond that at the Diels-Alder reaction. That is a little bit more of a problematic reaction that we'll have to deal with. But this one is pretty straightforward. 1 to 3, it's just like we saw with the radical. When we did the radical HBr, that it could add to the 1 position, what added anti-Markovnikov style, and could add to the 1 position or the 3 position because of resonance. Well, because we're adding hydrogen first, it can add to the 2 position or the 4 position of this conjugated diene. But okay, with that in mind, That's where I'm going to leave you for today. Have a good day.